So today I want to talk about a very simple but very useful theorem called Euler's Totient theorem, and the statement is as follows. Suppose we have two integers, a and m, that are relatively prime, so they don't share any other factors except 1. And suppose that we raise a to some k power, then this is going to equal 1 mod m if k is equal to the phi function or the totient function of m. And what that means is, so let's say we have the list of numbers 1, 2, 3, 4, all the way until m, every natural number before m. Then the totient function is the number of these natural numbers that come before m that are relatively prime to m. In other words, all the numbers that have a GCD of 1 with m. The number of those specific numbers is 5m. And to prove why this works, let's first consider what this set of relatively prime integers, how this set of relatively prime integers behaves. So let's just pick an example m to maybe make this easier. Let's say 9. Then this set of relatively prime integers is going to look like 1, 2, 4, 5, 7, and 8. Notice we don't include 3, 6, and 9 since they all have factors of 3, which share a factor with 9. And you'll notice that in the statement of this theorem, we get that a is also relatively prime to n. In other words, it's going to be, or when you take a mod 9, it's going to be in this set. And what that also means is that if you multiply one of these numbers by a, so if you have a, or all of these numbers by a, you have a, 2a, 4a, 5a, 7a, and 8a, this is going to be just a perfect rearrangement of this set mod m. And the reason for that is there can't be any intersections, and the reason for that is, let's say we had two hypothetically different numbers, x and y, and when you multiplied them by a, they were congruent mod m, right? And what does it mean to be congruent mod m? It just means that x times a is equal to y times a plus a multiple of m, so for some integer k. And since both sides of this expression are integers, we can divide by a, so we'll get x equals y plus m times k over a, and this part has to be an integer. However, a is relatively prime to n, so there's no way that any factor from here could divide any factor in n or in m, and therefore we can take m out and we'll just be left with this. X is equal to y plus m times k over a. And if we just replace k over a, let's call it k prime, we have x equals y plus m times k prime. But this can also be restated as a modular expression. In other words, x is congruent to y mod m. And we now have a contradiction because at first we stated that x and y are distinct mod m, except now that we've shown that they're not, that they're exactly the same. And so x and y can't exist. There can't be any pair of numbers that are different mod m which also multiply to be the same. And since we've now shown that these two sets are just rearrangements of each other, we can now think of what it means to be rearrangements. Well, what it means to be rearrangements, mod m, is that when you multiply all of the elements in each of these sets, so a times 2a times 4a, and this is also congruent to just multiplying all of the numbers in R without the A. So that's 1 times 2 times 4, on and on. And these two expressions are congruent mod M. And you'll notice that there's a common factor of all the numbers in R. And we can just divide by that common factor, and we'll have A to a power. Well, what power is that? That's just the size of R. And the size of R is what's defined as the phi of M. So we just have A to the phi of M is congruent to, well, since we divided all of this out, we'll get 1 mod M. And the reason we can do this modular division is, again, because every number in here is relatively prime to M. So like we did last time with the x and y example, it's only going to divide that imaginary k that we have. It's not going to divide into M. So we can make this division without any problems. And this proves the statement. We're done.